Thin lenses. A thin lens is a lens whose thickness is small compared to its radius of curvature. They can be converging or diverging. Converging lenses are thicker in the center than at the edges, and diverging lenses are thicker at the edges than in the center. Converging lenses bring parallel rays to a focus, which is the focal point. Diverging lenses make parallel light diverge. The focal point is the point where the rays would converge if the rays were projected back. Ray tracing can be used to find the location and size of an image created by thin lenses as well as mirrors. They have similar steps. 1. The first ray enters parallel to the axis and exits through the focal point. 2. The next ray enters through the focal point and then exits parallel. And 3. The next ray goes through the center of the lens and is not deflected. Again, you only need 2 of these in order to figure out where the image is located. In the first example, the object is located between the center of curvature and the focal point. The first ray enters parallel to the axis and exits through the focal point. The next ray enters through the focal point and then exits parallel to the axis. The next ray goes through the center of the lens and is not deflected. This is probably the easiest one to draw and will work for any kind of lens. Again, we only need 2 of these 3 rays to see where the image is. Now when the object is between the focal point and the center of curvature of a converging lens, the image is magnified because it's bigger, it's real because it's on the same side as the observer, and it's inverted because it's upside down. Now there might be some confusion as to whether this image is real or virtual. With a lens, the lens is placed between the observer and the object, so that when the image is real, it is on the same side as the observer and the opposite side of the object. It is a real image because it must be projected on a screen or a piece of paper. For the next example, the object is outside the center of curvature. The first ray enters parallel to the axis and exits through the focal point. The next ray enters through the focal point and then exits parallel to the axis. And the final ray goes through the center of the lens and is not deflected. Here we can see that the image is demagnified because it's smaller, it's real because it's on the same side as the observer, and it's inverted because it's upside down. And for the next example, the object is inside the focal point. Again, the first ray enters parallel to the axis and exits through the focal point. The next ray is a bit tricky. It's supposed to enter through the focal point and then exit parallel. But since the object is within the focal point, you need to take a ruler and line it up with the focal point and the top of the object. Then draw the ray from the top of the object to the center line, and then it will deflect and become parallel. That last one was not exactly necessary, since you can always draw the third one, which is a ray that goes through the center of the lens and is not deflected. As you can see, these rays will not intersect. Do you remember what to do if they don't intersect on one side? If the rays do not intersect on one side, you must extend dotted lines back to the other side. So now we can see that this image is magnified because it's larger. It's virtual because it's on the same side as the object, and it's upright because it's right side up. For a diverging lens, when the object is between the focal point and the center of curvature, we will now do diverging lenses. When the object is between the focal point and center of curvature, now the same rules apply, but these are a bit harder. Essentially, the opposite focal point is used. Since this is a diverging lens, the ray refracts away from the focal point instead of towards it. So we need to use a ruler and line it up. Now the first one travels parallel, and then it diverges away from the focal point. So you line up a ruler with the focal point and the spot where the parallel ray hit the center. The next ray goes through the focal point. The next ray goes towards the focal point and then diverges parallel to the central axis. Again, we need to line the ruler up with the top of the object and the focal point on the opposite side of the lens. The ray goes from the top of the object to the center of the lens and then diverges parallel. And the final ray goes straight through the center of the lens and is not diverged. As you can see, these three rays will not intersect, so we need to draw dotted lines back in the other direction. Now this image is demagnified because it's smaller, it's virtual because it's on the opposite side of the observer, and it's upright because it's right side up. Now if that object is past the center of curvature, again draw a parallel line and then a line heading away from the focal point. Next, draw a line that heads towards the focal point and then diverges so that it is parallel to the central axis. And then finally, draw a ray that goes straight through the center of the lens undeflected. And again, these three will not intersect, so we need to draw dotted lines in the opposite direction. This example turns out to be just like the last example, demagnified, virtual, and upright. And for the last example, the object is within the focal point. Again, we're going to draw the same three rays, first parallel and then away from the focal point. Next, towards the focal point on the opposite side and then parallel. And finally, we draw the ray that goes straight through the center of the lens undeflected. Again, since they don't converge, we have to draw dotted lines back in the other direction. And we get the same answer as the previous two, demagnified, virtual, and upright. So in that case, for a diverging lens, no matter where the object is located, the image will always be demagnified, virtual, and upright. The same equation that we used for mirrors also works with lenses. 1 over f equals 1 over do plus 1 over di, where f is the focal length, do is the distance to the object, and di is the distance to the image. And the same equation that relates the object's distance, image distance, magnification, and heights works for thin lenses as well as mirrors. A couple of quick notes about the sign conventions. The focal length is positive for converging lenses and negative for diverging lenses. The object distance is positive when it's on the same side as the light entering the lens and negative when it is on the opposite side. It's usually positive. The image distance is positive when it's a real image and negative when it's a virtual image. And the height of the image is positive when it's upright and negative when it's inverted.